In Kentucky, American icons buried in the dirt.
Made national and international news. It brought reporters from all across the country.
In Australia, tragedy strikes an epic Melbourne bridge.
You could see the bridge actually snapping in the center. You could see bolts coming off.
Big engineering shocks an Oklahoma town.
I just had visions of the entire downtown being leveled. Just feared the worst.
And in Canada, a near miss on a crucial river crossing.
I bounced, I hit the roof. I saw the bridge was collapsed.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. One basic rule of engineering is to build on solid foundations. But sometimes what lies beneath bites back. Like this catastrophic collapse in Kentucky.
I was in shock. I was in disbelief. It's stranger than fiction.
As 8 historic cars were swallowed whole.
This happened to be inside a building with millions of dollars worth of cars sitting on top.
It's a miracle the damage wasn't so much worse. America, known for its enduring love affair with the automobile, of all shapes and sizes. One of the greatest is the legendary Corvette. Owner and enthusiast Sean Preston explains.
What's special about a Corvette? Well, it's America's first sports car, and it's designed for the open road.
Named after a small, fast warship, the Corvette was inspired by Europe's small, fast sports cars.
Driving a Corvette, it's freedom. It feels like I own this part of the road, and me and the car are one. And I feel like I'm driving an iconic piece of American history.
In 1994, a museum celebrating this icon was built beside the Corvette factory in Bowling Green, Kentucky. Like the car, it boasted a distinctive look, thanks to the trademark Sky Dome.
You know, the Sky Dome is unique to the National Corvette Museum. You don't see this yellow structure and the red spire going through the middle of any building that we could think of, right? And it was done so that we could have a cathedral, if you will, to all things Corvette. Many of our unique pieces are kept in the Sky Dome. From each of the generations to one-of-a-kind prototypes, the Sky Dome acts as the shrine. It's an iconic structure with an iconic brand.
The unique Sky Dome towered strong and proud over the museum and its precious contents for the next 20 years. On February the 12th, 2014, just before 5:39 a.m., a burglar alarm was triggered inside the dome. Police rushed to the scene. Geotechnical engineer Mike Marassa was called soon after.
When the police arrived, they saw a great deal of dust in the air that they thought was smoke originally, so initiated a call to the fire department, who responded to what they thought was going to be a fire.
The CCTV revealed something much more shocking.
They neither had a thief nor a fire, but a massive hole in the middle of their iconic Sky Dome with 8 of their collector cars at the bottom.
The 10-meter deep sinkhole had swallowed millions of dollars of invaluable icons, and it continued to grow.
So when I arrived on the scene, the feeling in this room was surreal. The cars were almost like litter on the ground, this massive chasm of a sinkhole in the middle of the structure. The questions just kept mounting. How stable is the structure? How big is the problem that we're dealing with? There were way more unknowns than there were knowns.
Most concerning, the landmark red spire was in imminent danger.
It was hanging over the edge of the sinkhole, so the potential for any of this portion of the floor to collapse was pretty high. Had we lost the spire, it likely would have collapsed the entire structure.
The spire was only held in place by the steel connections in the roof of the dome. But the dome wasn't designed to support the spire. Who knew how long it would hold?
Mike and the team were in a race against time.
One of the riskiest and most immediate needs was to stabilize the spire structure. It involved supporting the structure with a steel element called a micropile.
These micropiles are steel cylinders about 1.5 meters long and 25 centimeters wide, which would be screwed together and drilled down through the cave into solid rock below.
The installation of 2 of the 5 micropiles that helped stabilize this structure were being installed immediately adjacent to the 35-foot drop-off. It was a risky operation.
Mike and the team worked tirelessly, and within a couple of weeks, the spire and dome were safe. Meanwhile, news of the collapse quickly spread.
Made national and international news. It brought reporters from all across the country. It brought geologists and cave experts.
And it was quite a circus of people that were walking around in amazement of this disaster that was at their feet.
The question was why, after nearly 20 stable years, had the floor collapsed? Kentucky's famous geology was an obvious suspect. Professor of Geoscience, Dr. Jason Polk, examined the wreckage.
One of the most cave-rich places that you have in the United States. We have over 5,000 known and mapped caves here. You can see extensively inside the caves. They can be literally 50, 60, 70 feet wide, 30, 40 feet tall, and they can go for miles and miles and miles.
This is Crump's Cave. It sits in the same rock as the museum and the nearby Mammoth Caves, the longest cave system in the world. All the result of soluble limestone.
Basically, the water is able to dissolve the rock as it picks up carbon dioxide in the soil and from the atmosphere, and it creates a really mild acid that over thousands of years dissolves the rock very slowly. And that in turn creates these large cave systems, which then become underground rivers, and it gets bigger and bigger and bigger until eventually it gets too close to the surface and you can have a sinkhole collapse occur.
Caves take forever to form, but the roof can collapse in the blink of an eye. You never even knew there was a cave there. And that's what happened with the Corvette Museum.
Looking at the Corvette Museum, you can see pretty clearly that this is the same type of environment where you had a large, massive chamber. Eventually, it's just its time, because it's the nature of the landscape for this rock to dissolve and for the rock to become too thin and for collapses.
Jason mapped the cave beneath the museum and discovered the sky dome was positioned almost perfectly above it. So how had engineers not noticed this before building the structure?
Generally, a typical geotechnical investigation would involve drilling through the soil and stopping once you hit bedrock, once you hit something hard.
In the 90s, engineers hit solid rock 9 meters down, and construction went ahead. So although it seems like a mistake to build here, they had no reason to drill deeper, and the cave lay undiscovered another 12 meters below.
So it's not anything that can be identified as negligence. Structural roof collapse of a cave is extremely rare. This structural collapse of the roof of a cave also happened to be inside a building with millions of dollars worth of cars sitting on top.
Now it was clear what they were dealing with. The team had another challenge on their hands: how to get the Sky Dome back in operation above an active cave.
The design team and the construction team sat down and went through a number of options. Everything from relocating this structure, trying to fill the volume of the cave with an incompressible material to stabilize the cave. And ultimately what was decided was to isolate the structure from the cave below.
First, horizontal sheet piles sealed the cave, topped with 4,000 tons of crushed rock. Next, just like the spire, micropiles were driven through everything, deep into the bedrock.
These hugely long micropiles act like a grid of solid stilts for the new Sky Dome floor to sit on. So the cave could grow, collapse, whatever, the floor would stay put.
Supported by foundations more than 30 meters below, the new Sky Dome floor was on solid ground.
So if the entire area were to collapse, the structure would stay intact because it is isolated from all of the geologic hazards that lie beneath our feet.
With the Sky Dome safe, the museum had turned catastrophe into triumph.
The red line denotes the actual sinkhole. So now I am standing on the part of the Sky Dome that fell 30 feet below me, bringing with it 8 of our beloved Corvettes. 5 of these Corvettes could not be restored. They're in their original condition, so we can honor them and also tell the story about what happened on that fateful day. And in fact, we've kept part of the sinkhole alive and well.
The new exhibit opened exactly 2 years after the disaster, and visitor numbers have gone through the roof.
The museum really embraced the tragedy and used it to their advantage, and to see it in existence, standing strong, it feels good. And I'm sure it'll last for a long time to come.
With massive engineering, how you build is just as important as what you're building. And when the technique goes wrong, results can be devastating. Like this disaster in Australia, where miscalculations led to catastrophic failure.
I heard the biggest crack I've ever heard in my life. It was just like a bomb going off.
A bridge tragedy that rocked an entire city.
The whole of Melbourne was in shock. In the blink of an eye, it's come down. She just could not believe it had happened.
And left a nation asking questions.
I was just horrified. What happened? How did this happen?
Melbourne, with a population of around 5 million, is Australia's fastest growing city. The River Yarra, which splits the city, has played a pivotal role in its success. Ken McInnes is a local historian and engineer.
Melbourne is one of the most cosmopolitan cities in the world. It has a huge diversity, a huge entertainment culture, arts culture, sports centre of the world. Without the Yarra River, there'd be no Melbourne. It provides water from the upper catchments, and then the lower reaches, where it's south of Delta, it provides support for Melbourne.
In 1978, this epic Yarra crossing opened to traffic. The West Gate Bridge. When built, the 336-metre central span was the longest cable-stayed span in the world.
Construction of the Westgate Bridge started in 1968. As a young civil engineer, I was very excited that this major structure was being built in Melbourne because it was the beginning of the mega structures, the large bridges at the bleeding edge of design.
As a budding engineer in 1970, Ken even visited the construction site and documented his trip.
That's span 10 and 11. And you can see the stage of the concrete construction on the temporary forward being lifted into place on the last 2 spans here, the central core of the bridge on the western side. There's a shot of spans from Pier 14 to Pier 15. So you can see the sort of construction. The workers' sheds are on the top of the bridge, and you can see how the derrick is then lifting the pieces into place.
Key to this mammoth bridge's strength was a tried and true technique dating from the 1850s, which would allow traffic to drive along hollow steel sections known as box girders.
A box girder bridge is a box. It simply is just a box which is continuous, and the box itself then spans from the pier to the pier, and it forms a tube which is strong.
The simplest way to build a bridge like this is to make individual boxes on the ground, then lift them into place, using temporary structures to support the load. Then repeat the process until the bridge meets in the middle. But this wasn't just any bridge.
With this bridge, because of the size and the weight of the boxes, the decision that was made was to build half of the boxes, assemble them on the ground, then jack them to the top of the piers, then roll them across into the structure, and then hope that the two longitudinal sections would join together.
Box girder bridges are always built in sections, and normally it's only the ends that have to meet. But here, because each span was split lengthways too, there was a lot more lining up to do.
Construction took place simultaneously on both sides of the river. Each half, weighing around 600 tons, would be hoisted into place, then bolted together using steel plates or flanges. Tommy Watson was a 22-year-old steel rigger when he landed a job working on the massive project.
It was the biggest job going in I think the whole of Australia when it first started. There was at least 3,000 people working on the job, and it was a good job for camaraderie and people working together. I was pretty proud to be working on the West Coast.
On October the 15th, 1970, 2 years into construction, Tommy and the team were working on the western side of the bridge, between piers 10 and 11.
That day was a Thursday, which in them days was payday, and everybody was excited. And we were transporting steel across, and I was working down the bottom, getting ready for lunch.
Up on deck, workers were preparing to attach the two half boxes that would form the span.
It was 10 to 12. Some people were on the toilet, some people were washing their hands, some people were in the lunchroom. I just turned around and I heard the biggest crack I've ever heard in my life, and I looked up and the whole lot just came down 100 metres from me.
With workers still on top, the entire 111-metre span between piers 10 and 11 collapsed.
You could see the bridge actually snapping in the centre. You could see bolts coming off. The concrete piling was cracking.
Around 2,000 tons of metal and concrete crashed to the ground and into the water.
I've probably seen 5 of my workmates either fall or jump off the bridge on the way down, and then an almighty thud just hit the ground.
They had shelters for the workers under the bridge. Some of those were squashed. People were thrown off the bridge, and the disaster happened.
The impact shook buildings hundreds of metres from the disaster, and the noise was heard around 20 kilometres away.
I just ran towards the bridge and it was just chaos. You realise that your workmates, the people who are friends of yours, were in that structure somewhere. I've never been in a war zone, but it's probably the closest I've ever been.
The catastrophe sent shockwaves across Melbourne. Local resident and construction worker Danny Gardner soon heard the devastating news.
You could not believe it. It was an absolute disaster. A lot of the people lived around here. Yeah, we knew who they were. And when you see that sort of tragedy happening, it was absolutely, can't put it to words.
This was the worst construction disaster in Australia's history. 18 workers were injured, and tragically, 35 lost their lives.
Oh, it was terrible. It was just something that came out of the blue, and it happened so quickly. And those sort of things, they just never leave you. You think about them all the time.
The tragedy left the nation in mourning. A royal commission was set up to investigate just what had gone wrong. and in August 1971 released its report. No blame was attributed to any one party, but the reasons behind the tragedy ranged from mistakes to miscalculations, errors of judgment, and failures of communication. Ken visited the site 2 months before the collapse.
I asked the engineer who was giving me a tour whether I could go up on the steel section, and he said, no, we've got some problems. So already I was a little bit horrified. To me, to build a box girder in 2 longitudinal halves and hope that the flanges would join at the top, you just wonder what people were thinking.
When the 2 halves of the span were rolled into position, ready to be joined, workers discovered that they were out of line by more than 11 centimeters.
Part of the problem was to try and get them to join. So they needed to tweak the boxes to try and get them to join together.
When you're talking about huge steel spans that are well over 100 meters long, 11.5 centimeters might not sound like much, but in engineering terms, it's huge. These girders had to line up.
To realign the girders, the decision was made to weigh them down with 7 8-ton concrete blocks. But the extra weight caused the steel to buckle.
The steel just wouldn't go back to the position it was. The concrete blocks really, they didn't work, so we pulled them all down and sent them away on trucks.
One of the solutions that was made was to tweak a couple of bolts to get a little bit of flexure in the boxes themselves.
To try to straighten the buckle, 30 bolts that held the girders in place were loosened and removed.
They took the bolts out and the bridge bent and collapsed, and having started to fall, the end of the bridge over the river then knocked down the pier as well.
Because the steel was under so much tension, it just snapped. I found out later that the steel had turned blue. They lost the holes. They're trying to put the bolts back in the holes.
In 1972, construction resumed, with many of the surviving workers returning to finish the job, Tommy included.
I started the job, I wanted to finish it. My mates got killed on a project that wasn't completed, and I wanted to complete the job for them too. The job had to be completed for the memory of the 35.
The steelwork was strengthened, temporary piers put in place, and based on calculations, this time no more than 2 bolts would be removed at any one time. Danny Gardner joined the rebuild as a rigger.
I am absolutely proud of working on the Westgate Bridge. I'm proud to be part of an iconic structure in Australia. A lot of our construction men who were killed in it were friends of ours. And that was a sense of finishing a job that unfortunately some of our friends' fathers couldn't finish.
More than 40 years later, the West Gate still stands proud as a vital crossing for the city, and a memorial to the workers who tragically lost their lives.
When I go over the bridge, I think about them all the time, and you end up in a traffic jam, and the traffic stopped, and you sit on the actual section that's collapsed. And that's the time I really think about the people's names.
My view of looking at the Westgate Bridge even today, standing here, I treat it as a monument of the men who were killed that fateful day. And if you look at it, it's a monument to them.
When engineering leads to catastrophe, the problem can be easy for all to see. But sometimes the most obvious suspect might not be to blame. Like this disaster in Oklahoma that literally made the earth move.
It seemed like it shook for at least 2 minutes.
As shocking swarms rocked the ground.
It's hard to believe that human activity caused this chaos.
Big engineering was in the firing line.
I just had visions of the entire downtown being leveled. Just feared the worst.
In the Green Country region of northeast Oklahoma sits the rural town of Pawnee. Brad Sewell is former mayor.
Pawnee is a small agricultural town. There's a lot of ranchers in the area. And really there's a lot of character and a lot of history in this town that's worth preserving and celebrating.
One important part of Pawnee history dates back to the time of the dinosaurs.
Millions of years ago, this area was underwater. Organisms die and eventually, over time, create products like oil and coal and so forth.
Oil was first discovered here in 1859 and quickly became big business.
People rely on oil for the economy and also oil-based products, cars and different things like that.
For decades, Oklahoma was one of the nation's leading oil producers. But by the 90s, reserves were becoming harder to tap.
In the good old days, prospectors would strike oil and out it would gush. But there's a lot more oil and gas underground that's trapped by complicated geology in so-called shale rock.
Engineers worked out decades ago that they could extract hard-to-reach oil and gas by fracturing the rock with high-pressure fluids. It's what we know as fracking.
Fracking starts like conventional extraction, drilling a deep vertical well, but that's where the similarities end. When drilling reaches shale, most wells turn horizontal and can extend for more than a kilometre. Next, special fracking fluid is pumped in under high pressure, fracturing the rock, releasing oil and gas, which flows back to the surface. From the late 90s, fracking operations opened up across Oklahoma, and state oil and gas production was back in business. September 3rd, 2016 started out as a regular day in Pawnee. Local rancher Mike Haslip was heading home when he got a surprise.
I had stopped to get a cup of coffee and a bite to eat, and that's when I felt the earthquake, and it seemed like it shook for at least 2 minutes. Of course, I had no idea where it was occurring. And I get in my truck and start heading back, and about 5 minutes later, I get a call from my then wife that told me that the earthquake had badly damaged our house. She said, "Wait, I've got to go. It looks like the barn's on fire." And by the time I got here, the fire department was here. There were fire trucks putting water on the fire. I have gasoline and a diesel tank, and they were trying to keep that from blowing up.
Mike wasn't alone. The quake had wreaked havoc across Pawnee and beyond.
It was frightening at the time because, I'd never experienced anything like that. And during the quake, I was wondering, is the house going to fall down on us? It was just really unexpected. I came right down this street, and this was the first building that I saw. And it was the most heavily damaged downtown building. And this facade right here on the south side had all fallen down.
Pawnee had been hit by the most powerful earthquake in Oklahoma history, measuring 5.8 on the Richter scale.
5.8 is a proper earthquake. Experts would classify it as moderate to strong. That's seriously shocking when you're nowhere near a major fault line.
In the wake of the devastation, the people of Pawnee were looking for answers. The most obvious suspect was fracking.
Well, the process of fracking, that has the effect of lubricating fault lines. And so areas which were formerly relatively stable, suddenly they don't have the resistance. And so you have the likelihood of earthquakes happening.
With no fault lines near Pawnee, there had to be another explanation. And there was. The problem wasn't extraction, but the cleanup process. Geoscientist Xiaowei Chen studied the quakes.
This earthquake is related to wastewater disposal, and the wastewater is a byproduct of oil and gas exploration. In this kind of area,
fracking uses millions of liters of fluid to fracture the rock. It also helps flush the oil and gas back to the surface. The problem is, all that fluid, called wastewater, is now contaminated. It has to be disposed of somehow.
For 1 barrel of oil, they will produce about 5 to 7 barrels of water, and those wastewater need to be disposed or get rid of. The most economic way to get rid of wastewater is to inject back into a deeper subsurface formation.
Wastewater wells go far below the shale, so deep that the water will be forever locked out of harm's way. Or that's the theory. The problem was, around Pawnee, the wastewater was much saltier than normal.
The salty wastewater was up to 15% denser than the existing groundwater, meaning that it could penetrate deeper into the earth, creating greater pressure on the surrounding rock.
The wastewater is being injected back into a deeper formation, and the formation here is about 1 kilometer deep. And this deeper formation is very close to what we call a crystalline basement that is brittle and can host earthquakes. So the problem here is that the injected water is close to the basement rock.
The so-called crystalline basement rock is hard and brittle. If you pump in unusually dense wastewater, the ground shifts.
It's ironic that the fracking process itself was relatively safe, but the leftover water wreaked such havoc.
The 2016 Pawnee earthquake might have been the biggest, but it was just one in a swarm of hundreds of quakes that started back in 2008. This wasn't a one-off.
Following the quake, residents demanded action, and state regulators ordered a reduction in wastewater disposal.
Hopefully, a combination of increased knowledge, monitoring, and regulation will bring a more stable future for the residents of Oklahoma.
This is a community where people have lived their whole lives, and it continues to charm visitors and residents alike. And I think it's worth preserving, and I'm glad that it survived the earthquake.
With big bridges, engineers strive for standout design. But when they get the materials wrong, the results can be catastrophic. Like this close call in Ontario, on a vital freeway bridge.
Late afternoon, transports were going north and south. All of a sudden, there was a loud crack.
A decades-old design flaw that nearly led to tragedy.
It was obvious. We had to report this there. It was major catastrophe.
This fail was far too close for comfort. Latchford, deep in the interior of Ontario, is proud to be one of the smallest towns in the province. George Lefebvre is former mayor.
It's a great place to live, and it's a beautiful location. We're nestled here along the banks of the Montreal River and Bay Lake. We're surrounded on 3 sides by water, which is quite unique.
The only way south out of town is over this 110-meter bridge.
It's extremely important because it's a landmark for our community. It's a monument to Sergeant Aubrey Cousins, one of Canada's 16 Victoria Cross winners in the Second World War, who was born here in Latchford. It certainly is a big deal in the town.
It's not just a big deal for Latchford. This bridge carries one of Canada's most important highways over the Montreal River.
This bridge allows Canada to be connected. Basically, it's a northern route of the Trans-Canada Highway, and it's absolutely vital to keep this connecting link to the north. Those magnificent arches are unique along number 11 highway.
Latchford's iconic crossing is what's known as a tide arch bridge. Although much bigger, Toronto's Burlington Skyway works the same way. Civil engineering professor Lydell Weeb explains.
Just like the Cousins Memorial Bridge, this is an arch-type structure. And the job of the arch, this curved part going over the top, that's really what's doing the work of carrying the load. The deck that holds the bridge, it's hanging from those hangers. They carry the load up to the arch, and then the arch carries it down to the piers on the two sides. The hangers are critical to this bridge because the deck can't carry the load by itself.
Bridge hangers do exactly what the name says. They might be steel bars, cables, or box girders, but whatever the design, the bridge deck literally hangs from them.
Latchford's bridge originally had 12 hangers on each side, suspending the deck from the twin arches. The hangers were connected top and bottom with giant bolts called pins. These connections allow the deck to sway with the movement of traffic.
Steel is super strong for supporting structures. But if you keep bending it and working it, the metal can start to fatigue. So lots of bridges have flexible connections built in. They are crucial to durability and safety.
Aubrey Cousins spanned the Montreal River from 1960. But after more than 40 years of loyal service, it faced a serious challenge. On January the 14th, 2003, during a ferocious cold snap, Jocelyn Roy was doing what he loves best, driving his rig cross-country.
Truck always been a part of my world. It's in my blood, this kind of truck here. Right now we're heading north. That's the direction I was heading to Oshawa.
Temperatures were 30 below zero, but Jocelyn was on a roll.
So just as I pull on the highway, another big truck was following me. It was a logger. Like we were coming on a good pace there. And right about here. It was right as we entered the bridge there. I heard a big boom. I thought I had a flat tire, so by the time I looked in my mirror, a bunch of snow fell, and when I looked ahead, my eyes kind of went down with the snow, and I saw the bridge that was collapsed.
The deck had dropped 2 meters towards the freezing Montreal River.
I bounced, I hit the roof, but then by the time I stopped, it was almost like 1,000 feet past the bridge. It was obvious we had to report this there, and it was major catastrophe.
Well, the deck of the bridge had dropped down. Basically, if you have a situation such as that, and if the traffic isn't stopped, death could occur. Much greater damage could occur to equipment, to vehicles. Anything going over the north end would have dropped into a gap, and anything coming from the south end would eventually have reached that point. The big concern was to ensure that nothing was coming north. Got it stopped, reported everything to the police. So it was a lot of reaction by a very few people to ensuring that safe passage was assured and that no vehicles got onto the bridge and caused further damage.
The bridge had failed. Luckily for Jocelyn, it didn't fully collapse.
The key is the word, because the way the collapse happened there, it kind of went in a V there, like maybe 4 feet on one side and 6, 7 feet on the other side. So it was just a slope, a big slope. And I was lucky. It could have been a straight fall right into the concrete pier.
But with the bridge down, motorists faced a mammoth 3-hour detour.
This might have been a relatively small bridge in a very small town, but the impact of the collapse was enormous.
People had to detour. They had to go down through Quebec or go over to Highway 144. Of course, for commercial transportation, they need special licensing to go through Quebec. So it was a real problem. All of a sudden, we'd lost our connecting link between Northern Ontario and Southern Ontario, between Western Canada and Eastern Canada. This is the Trans-Canada Highway. Well, it was a bad day for the whole Northeast.
Frustrated commuters wanted to know what had caused the sudden collapse. At just over 40 years old, the bridge should have safely carried traffic for decades to come. Engineering professor Lydell Weeb explains.
When you build a bridge, for sure you intend for it to last. It's very rare to have this kind of failure. When I go over a bridge, I'm not worried that it's going to collapse underneath me.
The reason for the failure was blindingly obvious. 3 broken steel hangers.
So the hangers are what are carrying the load for the bridge, and those hangers, over a number of years, they fractured. There were a few kind of stages to it. The first hanger is the one that seems to have gone first, and it seems like it fractured first and wasn't noticed for years.
Once one hanger failed, it was just a matter of time before a second, then a third. It might have taken years, but that bridge was only going in one direction, down.
The big question was what had caused them to fracture in the first place. On the day of the fail, temperatures had plummeted 30 degrees below freezing.
Temperature has a big impact on the performance of steel. Basically, when warm, it can be flexible. It can deform without losing its strength. It's called being ductile. But below a certain temperature, it loses that ductility and becomes brittle. Instead of flexing, it can crack.
But this area is no stranger to extreme cold, so investigators knew there must be more at play. Then they found something unexpected inside the arch span.
At the top of the hanger rods, where they were kind of hidden inside of the arch, there's a threaded portion, just like at the end of this bolt, and there are nuts on top of there to hold it in there. What the investigation showed was that for some reason, someone had filed down some of the threading in there. The reasons for that aren't totally clear. It could be to get rid of some defect that they saw, or it could be that that created a defect. But whatever the cause, that was where the fracture started, in the critical hanger rod.
Having located the source of the fractures, investigators realized why the damage hadn't been detected earlier.
When the bridge was built, the top of the hangers were enclosed inside the steel arch spans, so they couldn't be inspected, and the damage was never spotted.
Further investigation revealed yet another factor. The pins that should have allowed the hanger rods to sway were corroded solid.
What had actually happened is that the pins had seized, and so we start getting this kind of response in there. And you can see that when we do that, there's a lot more stress on the hanger.
With seized pins, the steel hanger rods were forced to flex rather than sway. It didn't take long for metal fatigue to set in.
Steel fatigues when it is repeatedly stressed or strained. If it happens over and over at the same point, the metal starts to degrade or fatigue, and ultimately it will crack.
What happens in that case is something like what happens with a paper clip. If I take a paper clip and I start bending it back and forth, I'm not strong enough to break this on my own in one go. But if I go back and forth several times, eventually this paper clip will break.
Damaged hanger rods subjected to decades of fatigue combined with the extreme cold finally pushed the bridge to breaking point.
So over a number of years, for all of these different reasons that we've talked about, we had one hanger that failed, and then that lasted a few years with no one noticing, and then another one failed, and again no one noticed. And then when the third one went, that was really what led to the failure.
The 43-year-old bridge was beyond repair. But with 5 decades of new engineering knowledge to draw on and lessons learned from the failure, the replacement is built to last.
With the new bridge, the solid steel hangers were each replaced with 4 steel cables. So not only are they more flexible, but if one should break, the bridge will continue to function safely until it can be repaired.
Today, the Aubrey-Cousins Memorial Bridge is once again carrying Canada's cross-country traffic in safety. And Jocelyn Roy is still trucking.
Yeah, I was lucky. We were all lucky. Actually, nobody got hurt on this one.
The people who drove over that bridge at that time are very, very fortunate and extremely lucky that they are alive today.
It's crucial that engineers learn from the past so they can build a safer future.